Swayam Prabha. Digital India. Educated India.
Good afternoon or good morning. After 11, they say good afternoon. So, okay, so we'll talk about what are the durability related issues in reinforced concrete structures and how do we design for it. Okay, how do we design for it? I'll talk about in the afternoon. Morning, we'll mainly focus on the corrosion aspects. What are the different type of corrosion which we experience in concrete structures, and also something which we usually neglect, which is about the type of steel bar which we use. And we only talk, typically we talk only about mechanical properties of the bar and not anything about the corrosion resistance and all that, and we assume everything is fine, but we find some challenges with that too. So that will, so these are things which we'll talk about in the morning session. So some of the slides some of you might have seen earlier also, but for the course we have to deliver those. So we actually are in a experiencing construction boom in our country, and when we talk about why do we worry about durability? Do we worry about durability? How? Raise your hand if you really think about durability when we talk about new structures. Okay, so I want to make this class very interactive if possible. Please ask question in between. Don't worry about the recording which is happening. That is mainly for other purpose. Okay, so very few hands were raised. What does that mean? Do we really worry about durability of concrete structures when we build them? Or you're only worrying about design for commissioning? Design for commissioning or design for durability? What do we worry about, or both? Tell me. Both, but the weightage for design for commissioning and design for durability, how much it is? Is it balanced? The silence speaks. Okay, so today we'll focus on the second part, design for durability. See, structure will stand because you have to get the money for whatever you spend. Client has to pay. They will not pay if the structure is not standing. Okay, we have something called defect liability period, right? Those who are in the industry, they know. How much is typical defect liability period? 5 to 10? Even there are projects with one. I think phase 1 of CMRL, it was 1 year defect liability period. Then they learned it is not good enough because most of the chemical related or the chemistry related problems of the concrete shows up after 1 year. By that time, you are already out of the defect liability period. Then you can't really do anything about it rather than fix the defect with additional money. This is the problem. So we need to really think about all the structures which we are building. We have to really think about how do we make sure that they are actually durable? Corrosion map, you can see here, coastal line, you have a lot of chloride, so it is very important to design them for durability. And we'll see why chloride only. Is it chloride only? Do you see any other terminologies on terms on the screen other than what are the important? One is the chloride coming from the ocean side, and then you also have carbonation. Okay, I had an experience with one of the buildings in our city, Chennai, where the building is about like 50 to 100 meters from the coast, and the problem was not chloride. Problem was actually carbonation. It's a silent killer. Okay, because carbonation happens when it is 60 to 70% humidity, which may be the case when you talk about 100 to 500 meters from the seashore. And depending on the pore structure or porosity of the concrete, you have to see, like chloride might leach out. It won't really enter into the concrete if it's too porous, but carbonation will happen. So it's not only chloride. Why I'm saying this is generally when people talk about corrosion, they blame chloride first. But carbonation is also something very, very important and we have to consider. We'll cover that also today. Now, why we really worry about all this is because it's cost a lot of money. If there is no financial impact, probably we won't worry much. Okay. Now, this chart is all over the place. Everywhere we show this chart. About 4%, 4.2 of the Indian, GDP is what we spent in India. I use the word spend, not invest. It's actually something which you don't get back. Okay. No, return is not there. So 4.2% is for India, very high. Look at Japan. What does it indicate? Japan is a small island, right? A lot of chlorides are there too, but their cost of corrosion is very less. So quest for quality. Okay, one thing is we learn everything in classroom, other is we try to implement them in the field. Two different aspects. So we have to actually build a quest for quality. Philosophy, but important. Yeah. Now, those numbers, how do we get? These are some statistics. See, because a lot of information is there. Some slides I'll skip very fast. Some slides we will go very slow. Okay. It's all printed and given to you. So this is just numbers, very large numbers. 50% of the structures actually experience a repair in how many years? It's a real data. It's not something which I cooked up. Okay. There was a major survey which we did about 10 years ago, international survey, where we got the outcome of the survey was like this. 50% of the structures. So if you talk to anybody, people are there in the construction sector here. I was told the other day that when you start a project, in the initial month itself, people will buy repair motor. Why do you need repair motor in a construction site? Huh? Whatever. Why do you need that? You have to build perfection or in the construction itself. You don't need a repair material in the construction site. That indicates that something wrong is being done. Okay, 30% of the steel which is made is used to replace the other steel. That means again the other steel has gone bad, so you are replacing that. Now gone bad means corrosion, nothing else. Okay, 40% of the cement is used for making repair materials. So there is a huge demand for repair, and the demand is coming up because the structures are deteriorating, either by corrosion or some other reasons. But today we will focus mainly on corrosion aspects in this class. But this is some reality which we have to really think. We talk a lot about carbon footprint, sustainability, etc. The best way to ensure sustainability is to build durable structures. If we can build with durability in mind, half of the job on sustainability is done, because you don't have to rebuild or you don't have to reconstruct the facilities. Okay, so now this is something like you can see this chart. How much is the percent? This is showing the reason for failure of concrete structures. Okay, but the scientists in there is a Central Electrochemical Research Institute in Karaikudi. They have done this study, market survey, and came up with this pie chart. How much is the problem with structural design related issues? 12%. Okay, the major chunk is that means most of the failure is happening because of either material related issue or construction related issues. So we really need to actually give more focus on materials and structure, construction aspects. It's very, very important. Most of the failures which we see is, it's not like structural design has, that it is perfected now. We have enough, we know how to handle that part. But materials, we still are learning how to handle it. So there is a lot of things to do in the materials and construction aspects. And now this is again, I said the material aspects. See the picture on the top right. That building, it's a building in Delhi, 30-story around, major towers, apartment complexes, and the condition, people have not even started living there. Before that, it reached that level. Why? They used water which is not good. Okay, so lack of respect for concrete. Lack of respect for concrete as a structural material. Anything can do this. People generally think you do whatever you want. Concrete, say, very resilient material. Okay, so this is not always true. Especially, I mean, you can't see, houses are something which people build, and it's like people dream goes into there, right? It's not like your cell phone or something which, or a shirt which you can replace without really, it won't change any of your lifestyle. But if you have problem with your house, imagine the people who bought houses in that apartment complex. So like that, examples are there in various cities in countries. So corrosion is becoming something very, very important, and in very hard way we are learning the issues if you do not care about material design. Hard way means you're losing homes. In Chennai, there was another apartment complex, about 500 families. In about 5-6 years, the house was the entire complex was demolished, because again same kind of issue. So it's something serious. I think we need to really worry about it. I forgot to put a slide here, but then later I put that saline ground. Why this problem is coming up? See, we take water, like why Chennai you have this problem. You take water from the ground. Okay, maybe 10 or 20 years ago, there was the quality of the groundwater was very good. But now we have taken so much of water from the aquifers and all that, and there is a seawater infiltration. So when you take water from ground, as you take, more water will penetrate laterally or infiltrate laterally, into the ground, and then you will actually be taking that contaminated water. What contamination? Chloride contamination. So it's not, the chloride is not only in the seashore. Okay, even after 15-20 kilometers away from the seashore or coastline, you can still have chloride contaminated water. So testing water is something very, very important. Okay, and let's say you talk about Rajasthan. Do you think there is chloride related issue in Rajasthan? Will there be issue? Yes or no? Raise your hand if you think no. 1, 2, 3, 4, 5, 6. Raise your hand if you think yes. What about others? Huh? None of the above. Okay. Actually, there are issues. Okay, the sand which you find in Thar Desert or even in Himalayas, for example, you might find chlorides. Maybe the content will be different. In Rajasthan, we have found that it is high. So another thing, like thanks for reminding that. See that map which I showed, it was just done. Let me go back. There is something wrong also in that map. So this map here, it's mainly focusing on the coastal belt. Okay. So just now I said about Rajasthan, you have issue. You go to Delhi, you have issue. So this groundwater is not considered in this. This is only airborne chloride which is considered. Okay, so this is, maybe next presentation I should remove this map. But good point. So we need to think about groundwater. That's very, very important. Okay, this is why I'm showing all these examples, is so that you can have, you will feel like, okay, there's something to do. See this picture here. Again, not very old bridge. Probably the bridge was designed for 50 years, but we started seeing heavy corrosion in just about 10 years, that means corrosion started well before that. Okay, and this is not something which you want. This is actually a highway bridge. Shankar would know about this. So tomorrow you can expect a question on that. This one, it's an apartment complex. You see how the granite slabs in front of the elevator is kept. What is holding it? It's a very good advertisement for the duct tape company. So strong that it can hold that granite over there. The reason is the steel inside that is corroding. You have shear wall there, right, around the elevators, and that had concrete which was contaminated with chloride. What happened in this case is, you can see the top right photograph there. What happened is the water body over there is actually a small creek around the buildings. They use that water and it is very close to sea. Okay, so water you have to really worry about. Yeah, go. There is 500 ppm is what we recommend. I think it says, right, 456, Shankar? 456 says, right, the chloride limit 5. No, which code is saying that? 456, no? Yeah, it says that 500. Internationally it is 1000, but in Indian case it's actually better. We say 500 as the limit, but I'll talk about that later when it comes to curing, because even 500 I think is very high, because I'll come to that later. So here you can see the picture on the bottom right. This is only like a 6-7 years old. Is this something which we expect from a structure? Now we are talking about precast, durability, all that. This is very good example of design for commissioning only, not for durability. Okay, so here what happened, like this limit, they didn't check the water quality, but the problem is, which one do you think is more of a problem, mixing water or curing water? Mixing water is not big problem, because you load the chloride only once, right? Curing water, how long you cure the concrete? It's more than the mixing water. Mixing water you put only once, right? But curing you keep loading it, and if there is a drying pattern in between the curing cycles, you get wetting and drying, and during drying chloride doesn't go out, only water evaporates. Next time you pour more water, you get more chloride in. So we have seen very clearly that curing water is more dangerous than the, it's more important to, I'm not saying more dangerous, it's more important to control quality of curing water than the quality of mixing water. Okay, and we generally think any water can be used for curing because it's happening at the site. Quality control is less. This is again why probably precast is good, because it will be done in a controlled factory environment where you can control everything more meticulously. So the whole idea of precast is move everything from site, or maximum from site, to a controlled factory environment, so that minimal work is happening at the site. Okay, but we need better planning, but many other things are there. Okay, so now coming to service life, you have two different aspects mainly. Forget about the repair part. I'm talking about the you can see 1 and 2. So totally there are 3 phases. The 1 and 2 is what we really worry about in the beginning or at the time of design. So which one do you think we should equate to? So when you say service life of a structure, is the length of the initiation phase or the initiation plus propagation phase? What do you think we should consider? Initiation is the time taken for the steel to start corroding, or to be precise, the time taken for chlorides or carbon dioxide to travel through the concrete cover, reach the steel surface, and then initiate corrosion. Okay. In the examples which I showed earlier, that was 0, right? Because you had contaminated, chloride contaminated water. So day 1, it starts corroding. It took 5-6 years to show up as cracking and spalling and all that, but it started on the day 1 itself. Here I am not talking about that example. Here we are talking about good quality concrete, which is made with good quality water, but eventually the airborne or the chlorides will ingress into the concrete, okay, through diffusion. So that process is what we are talking here. Okay. Now, if you talk about typical structures, let's say 100-year design life, you're talking about a structure. Okay. Ideally speaking, the 100 years should be equal to the initiation phase. Typically, we say if you look at any software available for service life design, the propagation period they consider will be anywhere from 2 to 10 years, not more than that. Because once steel starts corroding, we know that it doesn't take that much time for the concrete to crack and spall, and then lead to severe capacity reduction. So for all practical purposes, if you're talking about long life, let's say multiple decades, it's better to consider service life as time for corrosion initiation. The other thing is, I would say, bonus. The propagation time is bonus time. That's how we should do. Okay. Now that you see the blue arrow there, which shows the red circles are the chloride ions. The blue arrow is showing the direction by which it passes through the concrete cover. The black circle is the steel bar. Now, if I want to design this, you can imagine one of the red circles to travel from the surface of the concrete, travel through the cover depth, cover thickness, and then reach that black circle. How long it should take? Let's say we are talking about 100-year service life for a major bridge. It should take that much time to travel. Now, what is the typical cover depth we provide for a bridge element or let's say building? In this class, we'll talk about building. What do you think? On a column, you have a RC columns, 40 mm. So, and maybe a house I will not design for 100 years, right? Next generation may not like the one you built. So there may be other. So let's say 50 years. Okay. Now, if I want that column to be free from corrosion for 50 years, I should make sure that the concrete used in the cover is so good that it takes 50 years for these chloride ions to travel by that 40 millimeter travel distance, reach the steel, build enough, built up on the steel surface. So, and it's not that one chloride ion reaches the steel, it starts corroding. No, there is also something called chloride threshold. It's written over there, which is the minimum amount of chloride required to initiate corrosion. Okay, this is a very important parameter when we talk about chloride threshold. It's one of the boundary condition you can think, and this whole problem is solved using finite element or finite difference approaches, where they use this boundary condition is the chloride content at the steel surface should be equal to or less than chloride threshold, so that steel doesn't corrode. When it hits chloride threshold, it will start corroding. Mostly those things, yeah, these are all considered, but I don't think it is considered to the best level possible, because whatever is there in IS code right now is based on technology available or knowledge available in 2000. So we are next revision, you will see a lot of significant changes, and there is an exclusive chapter on design for durability. But this year it will not come. It will be next year or see the cover thickness. It's not like one parameter. You have to look at the travel distance, which is cover. How much is the chloride available outside? Let's say you're talking about seawater or some condition, that is another, that is the top surface over the top chloride, CO2, RH, all that exposure conditions. Okay, travel length, and also the type of steel and concrete which you use. It's not only a parameter of steel, it's also a parameter of the steel and concrete, the resistivity of the concrete. All this plays a significant role. So these are, and it's not very easy to bring up all these things into a small equation, but efforts are there to actually be, because to be able to design with some conservative approach. Okay, so you will see changes for sure, but that's how it is right now. But there are software programs available which already consider all these aspects. Why do you want to reduce the cover? I want you to ask this question at the end of this lecture, at the end of the afternoon lecture, because that's exactly, we are talking about cover. Cover is something which is the most important parameter. We don't want to reduce that. See, theoretically speaking, you can reduce. That's the main concern. John, you have a new cementitious material coming in, so possibilities are there. So cover, I think we don't want to reduce the cover, ideally speaking. Because if you reduce, again, you will have trouble in filling that space. The coarse aggregate size should go around the rebar, right? If you make it thinner cover, if you reduce the thickness, it's going to create more problem. No. You're telling after you're talking about new construction or structures which are already built. During construction, you should put an extra person to take care of cover. Yeah, more number of cover blocks in the. Yeah, that is not somewhere you want to, relax. Yeah, that's where you have problems. So I think we should change our mindset. It's very important that you brought this up. We should change our mindset and think what is more important, and don't cut corners on that. Why they are not using? I didn't put a slide on that. It's another topic. This is actually something which we don't want to worry about. You asked that question in the right place. Okay. Corrosion resistant bars. This is like, metallurgists sell the rebars, right? Not civil engineers. Who sell it? Steel companies, they are all metallurgists. For them, corrosion rate is something which is used for assessing quality of a metal. Okay, but in civil engineering, I don't worry about corrosion rate. Why? Because this orange region, initiation phase, that is a time when steel doesn't corrode. Steel is in passive state. When it corrodes is the red phase, and that I don't want to consider in my design. So they are selling steel saying that it is corrosion resistant steel, because we did some studies on chloride threshold of corrosion resistant steel and other steel. We couldn't see much advantage, but corrosion rate is low. But my concern is more about chloride threshold or pH threshold than the corrosion rate. So you're actually spending more money on corrosion resistant steel. In fact, that term will be removed in the upcoming code, because you cannot specify a product saying that something visually you can say, but one has to test, and then only you can say it is corrosion resistant. I'm selling as corrosion resistant, but whether it is corrosion resistant or not, I don't know. So you can say high copper steel or maybe something like that, but you can't actually sell it as corrosion resistant steel. I think it's a misnomer. It's not the right practice. Why should we listen? That's our problem, that we are listening to them, right? That's why I don't like recording. We can't. Okay, so this is the problem. You might have seen elephant hanging on the bar, right? There is advertisement where you have an elephant hanging on the bar, and it's like Paul Walt. So these are all marketing gimmicks. Engineers should not fall for it. You should know what parameter you should look at, and what is, you should not accept that. Okay. So chloride threshold is something very important. So this corrosion rate is not something which we want to look at. We want, when you assess a rebar for durability, you want to look at chloride threshold or pH threshold, which defines the initiation phase, okay, which is much longer than the propagation phase. If you're talking about 100-year life, why do you worry about that last 10 years which you will get? You need to worry about the first 100 years. Okay. So corrosion resistant bar, I say it is not required. So you have to rethink about on those. Yeah. Yes, it's already there. I will show some of the examples in the coming slides in the afternoon, but it's already there. It's, see, we are too late in implementing. So the penny, see, it takes, we're talking about diffusion here. So the new technology also takes a lot of time to diffuse into the market. There is very high resistance against the diffusion of technology. We tend to ask 100 questions before start doing something, and those questions, it's very difficult to actually implement something. Rather than, I mean, I would say writing journal paper is easier. Doing experiment in the laboratory is very easy. But getting something done in the field is the real challenge. Okay, so it's there, technology is there. In fact, Shankar, you want to talk about that bridge? When those slides comes, I'll invite him. Okay, so here you can see what do we do, how do we do. One is concrete, other is steel. Okay, you cannot say, okay, I'll use best quality concrete and I will not worry about steel. It's not going to give you a solution. Both have to be, the quality of both have to be balanced. The system is the one which gives you durability. You might have heard again, like Professor Ramlan was saying, advertisements, how do they, fool people? Durable cement, you might have heard that, right? Durable cement or earthquake resistant steel. Steel cannot be earthquake resist. The steel concrete system which we have to design, depending on how many steel and where you are putting, it gives you earthquake resistance, right? So ductile steel is okay, but you can't. So again, we as engineers have to think what to believe, right? So earthquake resistant steel, no. Reinforced concrete system with good quality concrete and good quality steel can give you earthquake resistance or durability. That is possible. The system is what we have to look at. Okay. So both are important. It's not only cover. So here you can see when we talk about design for durability, not for design for commissioning. Design for commissioning, you worry about hotcrete. Okay, that is the concrete inside the steel bars. In all your structural design aspects, you consider that concrete, right? Which is confined concrete inside the bar. But when it comes to durability, I am not worried about that because I know the other engineers will ensure that good quality for the hotcrete. My worry is more on the what? Speak up. Covercrete. So design for commissioning is influenced by the hotcrete. Design for durability is influenced by the covercrete. So if any new construction site, if you see, and if you see that the concrete is dry in the early few days, that means it's not getting cured very well. It's like you buy best vegetable in the, find out best shop, get best vegetables, cut in nice face shape and all that, and you put a poor chef, or you increase the flame, you will not get good dish, right? So cooking is very important. So here we say cooking and curing. It's essentially giving enough water for the outer or peripheral concrete so that it reacts very well and you get good quality cover concrete. So there are products, the people in the from the site here, like there are special foam releasing oils available, or agents they call it. Okay, you will see very smooth finish if you use that, because all the air bubbles which gets trapped between the concrete and the formwork gets released, so that you get nice finish on that, which usually you will not get with the typical waste oil which is coming from the which is widely being used. Okay, you won't get that good finish. So if you want glassy finish, you can use some of these products. You will actually get in. Lot. That's it. They have repair products there in the construction site. Okay, so now in fact, I should share you this experience. See, in some of the sites, you will see brown color rebar lines when the formwork is removed. About several years ago, I thought it is actually rust. Okay, and this happened right in front of Chennai airport. So I saw this, and then I went there, and then I argued like anything. No, it's why it is corroding now. And eventually I found that it is the foam releasing oil which they apply, and that oil was applied on the rebar, and I mean not the right way of doing it. Instead of putting only on the plywood, they also put it on the rebar, and that dripped and reached the plywood in excess quantity, deposited, and when the concrete was placed on top of it, and then when the formwork is removed, this brown color oil is there. So we should, I mean, lot of such things, in the field you see, but that's not the right way of doing it. The formwork releasing agent should not be put on the steel. Steel should not have any oil on the, when you place the concrete. It should be very neat and clean. In fact, spray water like anything on the steel before the concrete. So that will remove all the dirt. Anyway, coming back to corrosion, what is corrosion? If you look at how it is made, how steel is made, we use iron ore or scrap metal, whatever. We make steel, like in India, even today, all the rebars are made, most of the bars are made, 99% it is made using iron ore. Okay. Sometimes these iron ore are coming from either African countries or even Australia. All that is, it's not only our own materials, we import materials also, and it is steel is made. In the US, they use 98% of the steel bars made are using scrap metal. India, slowly we are starting to make such steels because we don't have, I mean, we are getting scrap metal from the automotive industry, melt it again, and then make the new steel. Quality is very good. There is no issue with the quality. I just want to tell what is happening in our country nowadays. But most of the bars today are made through this route, what you see here. Okay, blast furnace slag, and then you melt this material. So that means you are giving more heat energy to the metal. Okay, and then if you want a particular shape, it is passing through some dies and then getting into that shape. That is where you use a lot of mechanical energy. So the steel has much higher energy than the or the raw materials, because you have more heat energy is being supplied and more mechanical energy is being used. Now, when you have something at a very high energy level, what will be the tendency? Anything you raise something, if you leave hand, it will come down. So the energy level has to come down. There will be a tendency for that. Like after lunch, what do you want to do? Sleep. Okay, so you want to rest. Steel also want to go back to the lowest energy level possible. So it will try to react with the immediate environment, and that reaction gives you the chemical reactions which you see on the bottom left. That gives you again some products which are of similar nature, chemical phases, like the iron ore. So corrosion is nothing but extractive metallurgy in the reverse direction. Okay, you make steel by putting more energy, and once the structure is made, it will try to go back to its lowest energy level, and that's what essentially corrosion is. Okay. Now, what is steel? Generally, we think it's very homogeneous. It looks like very homogeneous material, right? You look in microscope, it will look something like this. Okay, different phases, black dots inside a white region, and then you can also toward the center of that picture you can see some parallel lines over there. So there are different phases. It all forms depending on the chemical composition and the way in which you cool the molten material, the rate of cooling, how it is being cooled, all that will lead to different elemental phases inside the steel. Now, good thing is that this material has very good resistance against, it can have very good resistance against corrosion. Tested and proven, and mechanical properties are very good as we want. So all that is possible with the addition of all these elements. You can see a long list of elements there. Small quantity, but they have their own roles in achieving various mechanical and chemical properties of the steel. Okay. Now, concrete is something which has very high pH. Yesterday or day before, Professor Librata was talking about one compatibility between steel and concrete. What was that? Strain compatibility, or the coefficient of thermal expansion is similar. That is a mechanical parameter, I can say. Now, another compatibility reason is this, chemical compatibility, because steel will not corrode if the pH is very high. Okay, your hand, you put in water, will something happen? Nothing will happen. Put it in acid, you may not have the hand again. Put it in highly alkaline solution, will something happen? It will burn. Very high pH. So more away from the neutral point, pH neutral, you have problem. Your skin is not stable. It will start reacting. Okay. But steel likes the high pH. It is very stable in very high pH environment. This is the reason why we are able to use steel in concrete in terms of chemistry. So in addition to coefficient of thermal expansion, that is mechanical, this is chemical reason why. So there are two compatibilities. Okay, why we are able to use steel in concrete. Okay. Now there is something called Pobbe diagram. This is 100-year-old diagram. Okay, where it shows at what pH condition the steel will be in active corrosion state, or will be in a passive corrosion state, or an immune state. Means there is not even a passive film. Okay, I'll come to later what is passive film. But the yellow box over there is where our concrete is. Okay, so when you put steel in concrete, that typically this will be in that yellow box region approximately, and that region provides the passive state for the steel. That means the steel will react with the concrete. It will form a very thin layer on the steel surface. And when I say very thin layer, the thickness is in angstroms, not even nano. Okay, few molecules, that's all. So that thin layer will prevent the corrosion of further steel. Okay, so this is passive film. So you can show, I put that as a green line over there. It is to, this Statue of Liberty, right? What is the color? Green. At home, if you go, you will see some old vessels which will have some green color patina. That is also oxide of the metal. Statue of Liberty, the green color is oxide of the metal. Okay, it's not paint. Like now we have Statue of Unity, right, in Gujarat. That also will change its color every decade. It will change to green, then eventually in 100 years or something, it says it will be violet in color. So you will see over a period of time, Sardar Patel will change his color. Okay. So that's the metal which is used. It's not concrete. What you see is not concrete. Okay, the metal. That metal will react and that oxide layer. So like that, that is what the passive film is when you talk about steel in concrete. And this film has no color. When you talk about steel in concrete or the steel surface, the passive film is not green. I put green here just for you to compare. But it is colorless, very thin, but it gives that protection against the further corrosion. Okay. Now, before going into chloride and carbonation, do you have any question until now? No, that's a new structure, new phenomena. It is beneficial. People also use it, and it is much better than using chloride contaminated water for sure. But you have to compensate for the strength. Curing compound typically does not, the efficiency of curing compound, it's about 80%, let's say. In other words, if you're talking about 100 MPa concrete, in moist cure condition, if you get 100 MPa, if you use curing compound, you might get around 80%. So you have to compensate for that. That's all. I think, but that is still a better way than using water which is not good. And over the piers is where engineers don't go up and check. If you go any of the, even metro, I have seen some of them, you go up, you will see rough concrete surface like waste concrete, everything will be there on top. You want the top surface to be with a little camber so that even the rainwater comes, don't rely on the pipe which is provided, but try to get the water out. So design for water repulsion or resistance is also another concept, like design for commissioning, design for durability, design for water resistance, design for maintainability. I have not included this in the slide, but this I think is very, very important when we think about long life for structures. 4 things, 4 design approaches. Maybe 5th one is design for functionality. Okay, but yeah, so we have to, like that pillar over there, you have the bench, the horizontal member. On top of that, you don't want water to stay. That's what Professor was mentioning. You don't want water to stay there. So we provide a little camber. In precast, it is easy if you go with precast members, but that's cast in situ over there. But I'm saying if you go with that, you can actually do everything. At the factory, you can design for all these fine detailing. To do these things in the site is very difficult. Okay, so when it comes to corrosion, basics, there are 4 components. Any corrosion cell, if one of these 4 are missing, the corrosion cell will not exist. In other words, it's a open circuit. So you will not have any corrosion. Okay, think about the battery which you had. The typical battery. You have an anode, you have a cathode, and you have a which connects the anode and the cathode for the ionic conduction and for the electronic conduction. Sorry, for the ionic conduction and for the electronic conduction. So the gray portion here, imagine now it is steel bar. The yellow is the concrete. Now, if you have corrosion happening, you will not see that the entire bar is corroding. Okay, at one point, at one time instant. I'm not saying you take a bar which was getting corroded for 10 years, you will see corrosion everywhere, right? But at one point of time, the corrosion reaction will be, there will be a few anodes, few cathodes, and the connection. The bar itself plays the role of the electronic conductor, and the concrete plays the role of the ionic conductor. Okay, this is how it is. Any corrosion reaction, this is how it is. Now, this anode and cathode need not be the same bar. Imagine you have a slab, okay, or a column, whatever it is. One side you have more chloride, assume, and the other side does not have enough chloride. Now, the side which gets the chloride first will become the anode, and the other side, the bars on the other side will become the cathode. Let's say you have a slab, you have a top mat and a bottom mat. Okay, if the chloride is coming from the top bar will be anode or cathode? Anode. Bottom will be cathode. What is connecting the two? Where is the electronic conductor? No, electronic conductor. The stirrups. The stirrups, if it is connected, they will play the role of the electronic conductor, and the concrete will play the role of the ionic conductor. Okay. Now, that is a case when we are talking about old concrete. Means the resistance of the concrete is very less. Today, when we talk about concrete, if you have fly ash, slag, silica fume, etc., we have very good quality concrete, which has very high resistance. In such case, the only top mat will have both anode and cathode. Bottom bar may not play a role because the cell is formed on the same bar. In old concrete with porous concrete and all that, you will have cell formation. We call it macro cell, big corrosion cell. When you have new concrete, we call it micro cell. Okay, and in the micro cell, the anode and cathode will be right on the same bar, very close to each other. Okay. Now you can see here anodic reaction and cathodic reaction. Is it getting bored? Chemistry, anode, cathode. Little bit boring. Long gap. That's why I'm going very slow. So you can see this palm tree on the right side. Is it palm tree? What do you see? It's a reinforced concrete pile. You can see the steel bars stirrup there, but the cover is gone. What do you think is the reason for that loss of cover at the point where it is coming out of the water? It's written alternate wet and dry. Why it is a problem? What, like wetting and drying happens? Can you think why it is aggravating the deterioration there? So let's imagine the water level goes up and down, and whenever it goes down, you have what happens? The water that evaporates, right? But assume that chloride is still there. It stays back in. Next cycle, again, water will evaporate, but the chloride which is already there will not come out. It will stay back. Some leaching will be there, but mostly it will stay back. Okay. So that region, wet-dry region, if you look at the chloride profile or how much chloride is entering into the concrete, it will be more than the remaining region. So wetting and drying is more severe when it comes to ingress of chemicals into concrete or ingress of anything into the concrete, okay, than the fully submerged case. If you want to relate, if you go deep down in the ocean, you will still get the remnants of Titanic, the ship. Even after 100 years, it is there. Why? It should have corroded and dusted, right? Why? Because there is not enough oxygen, so it's not corroded. That is what is happening at the, if you go deep down into this pile below the water, you will not have oxygen. Typically they say about few meters below the water surface, like the surface of the water, you will not have enough oxygen to sustained corrosion. Okay, not like few centimeter, couple of meters below. If you're talking about ground, 1 or 2 meters below the ground level, you will not have much corrosion. But up to 1 or 2 meters below the ground level, you will have enough oxygen and you will have enough moisture, and you can have good corrosion. I mean, not good corrosion. I don't want it to use the word good, but you will have corrosion. Okay. So point here to note is at the anode side, you have metal dissolution. Metal loss is happening at the anode. Remaining portion helps the anode to corrode, which is the cathode. Okay, so if some metal, if you look at, if something metal loss is happening, that is the location for the anode. The surrounding region which has not corroded much is the cathode. Okay, any question on this? So it's very clear on this picture. If you go above the wet dry region, you may not have enough oxygen. Sorry, you may not have enough moisture. If you go below, you may not have enough oxygen. So in the yellow equation over there, you have oxygen and moisture as the reactants, right? Now, if one of the reactant I take away, what happens to the rate? Chemical reaction rate, it reduces. So that's what happens in most of the cases. So either water or oxygen, keep it away from the structure, you will be better off. But it is very difficult. So better to make the concrete in such a way that we can keep the water and oxygen away from the steel. So concrete gives very good protection. So this is the another schematic to really, understand what I just told. Which is the anode location? It's written there where the steel is lost, right? And then you have the, what is happening? Fe2 plus getting into the water means iron is being lost. Metal dissolution. Okay. Now you also have anode, which is written on the top left, that same equation which you saw in the previous slide. That is happening. That is taking all this negatively charged, negative charge. See, electrons don't move, okay? They transfer the charge. Like imagine if you have 10 people standing in a line, and then if I want to transfer one bag of cement from there to there, what do? Will people carry the cement bag, or they transfer to the next guy? Pass it on. That's what happens in the case of the negative charge exchange. Electrons don't move. They transfer the charge to the cathodic side where you have enough moisture and oxygen, and that reaction product is what of the cathode reaction? What is the product? It's written on the screen. Hydroxide ions, OH minus, right? That OH minus and the Fe2 plus will combine to form rust, ferrous hydroxide. Okay, so that's what is our rust. I think this basic falling only, like the just cracking. Okay, anyway, why this cracks? Because when steel corrodes, it expands by 6 to 8 times. Okay, now where the steel, the rust will occupy, it will try to push. That's essentially what is happening. Okay, it will try to push and it will lead to cracking. This I have all these slides. I'll share with you. So 6 times increase in volume. So if you, it's a very good deal. You buy 1 cup of steel, you get 6 cup of rust. It's a good business. But nobody will buy rust from you. People will buy only steel. Now this is a picture I took to show that, how much pressure is exerted. This is from Croatia. You can see that square shape iron piece, Roman, which is probably 400 years old, right? It's a Man-made rock or natural rock? It's a rock piece. Concrete is man-made fall. It will fall down. And then still we will keep looking at it. Okay. So now this is again another building where you can see along the staircase you have severe spalling. Why the beams on the remaining part of the building is not corroding like that? Water? Where is the source of water? No, here it's not. Rainwater is everywhere. Entire building should get rainwater. Clothes. Where they put cloth over there, you supply water. ACs will be on the sunshade. So this is a new phenomena. See, up to about maybe 10-15 years ago, we might not have been using AC much. So on campus, we did a study, this campus, on how many sunshades are cracked because of the water from the AC. We found 76% of the sunshades are cracked. And this was not happening for 1959, or let's say 60 until 2010. That is when we started putting AC on the sunshade. And monkeys on campus break all the pipes and then let the water fall on the AC, or fall on the sunshade. So you supply water throughout the year. And if that water is chloride contaminated, even in small rate, when you supply that throughout the year, you will actually create problem. It will build up, the chloride will build up on that. So this is again for everybody, it's a new phenomena which will not be in any textbook. This AC, water from the AC and this kind of thing. So you have to see, now if you want to repair this, people will say entire building, let us paint, waterproofing. No, I mean only targeted treatment. Do only where you have problem. If I have problem on this finger, I don't need to put band-aid on the right side. Okay. So because why I'm saying that, usually when people go for repair, they spend a lot of money unnecessarily. So if you really step back and think about the root cause of the problem, you might be able to do the repair at much lower cost. Okay. So we'll key factors which influence corrosion, if I want to summarize what we just talked about. One is essentials, and then you have assistants, and then you have protectors. Essentials are moisture and oxygen. Okay. Then what are the assistants? If you have moisture and oxygen, it is not a problem. If you don't have chloride or don't have CO2, then steel will not corrode. If you put steel in lime solution, okay, you might have used in the lab, right? You know, for curing concrete, you use lime solution, right? Same solution, if you put steel in that, it will not corrode. Why? pH is very high. So at high pH, steel will not corrode. Okay. Problem is when you use normal water, where the pH is low, passive film will not form, and that is it corrodes. So if you have, you know, water tanks, if the pH is maintained, it doesn't matter, it will not corrode. So water is not the problem. My problem is my assistants are the problem. Okay, assistants to corrosion, chlorides and carbon dioxide are the problem. Okay, then protectors, you have to have proper cover, and if you are repairing, do a proper repair, durable repair. That we'll talk later next week. So today mainly cover. Okay, that's the main protector. So don't cut corners on cover. It's very, very important to ensure that cover is adequately provided as per the design drawings. See, one more thing, if you have enough cover, even if the steel starts corroding, the rate of corrosion will be less. Why? Because imagine a case where you have very small cover, one case, and another case you have thick cover. Now I have a 1-day rain. Suppose it rained for 1 day. This one with thin cover, the steel inside that will get water. But the one with thick cover may not get water. Corrosion happens on the steel surface, not on the concrete surface. So cover is something which we should not neglect. Okay. So whatever it takes, make sure cover is adequate. Many other problems will be resolved. So this I already covered. So carbonation and chloride induced corrosion, two types of corrosion. Okay. What is the difference? In the chloride, you have kind of no pitting, uniform corrosion loss, whereas in the chloride, you have pitting corrosion. Okay. Yeah. I have a slide in the afternoon on that plaster. It's only cosmetic. Plaster is only whatever we could not do on the concrete is covered by plaster. It's a patch. Only architects will like it. Usually no, because I mean it's not. It will be very costly if at all it is there. The reason is you have more surfaces there. You have sand or very fine particles. So the binder, there is a lot of interfacial transition zones. So the penetration is much faster in plaster compared to concrete, because concrete I have rock pieces which will block. So like the similar way we talked about the service life, in case of carbonation, it is the pH threshold. So this slide also I discussed a little bit. So imagine all the cars over there are pumping CO2 out, and that is getting closer to so the immediate surface for the concrete beams over there or the concrete elements over there, it's rich in CO2. Atmospheric CO2, when you say 0.03 to 0.04%, that is far away from the city. Okay. Right here, if you go there and measure, you will see very high, close to 1000 ppm. We have done that measurement. Okay. We have done something at, from the seashore in a car, we drove and then measured people, CO2 level along the roads, and it's very, very high. Okay. And if there's relative humidity inside the concrete is around 60 to 70%, that is the worst scenario. And most of the case, it is like in Chennai, it is like. If you go to Delhi, maybe not. It will take long time to carbonate because it's very dry environment. If you go to Hyderabad, maybe not. So you have to look at the ambient humidity condition to see whether I should worry about carbonation or not. So when all this, why I'm saying this, material selection, you have to think multiple aspects. Okay, it's not just one point you take and then make a decision. No, you have to think about exposure condition. What is the life if you want? If I want to build something for 10 years, I don't worry about all this. But if I want to design something for 50 years, I have to worry about. So the same structure element, if you put in Chennai, it may have 50 years life. You move that to Hyderabad, it may even last for 100 years. So depending on the exposure condition. And again, I said Chennai and Hyderabad. How about if the Hyderabad is a chloride manufacturing plant or HCl plant? So immediate environment is what you have to look, not just the geographic location. Okay, so a lot of things are there. Now this, many of you might be familiar with railway station. And if you see, I have talked to railway people, they said like every 2-3 years they change this. Imagine there are 7,000 railway stations in the country, and then how much waste you are creating with this. Okay, this is just motor with a rebar in one very thin 6 mm diameter rod inside. Very good example of carbonation induced corrosion. It's not nothing to do with chloride, and this is something which we should not practice if you want longer life. Again, you might say this is not a major structural element, but it is creating waste, which we have to manage later. So what is carbonation? Carbonation is essentially, you see the yellow equation there, you have a high pH contributor, which is calcium hydroxide in the concrete, that reacts with carbon dioxide, giving you something. Now, when this reaction happens, what happens to pH of the concrete? Look at the equation and think and tell what happens to the pH of the concrete. It reduces. Why? Because I am consuming what am I consuming? Why the pH is decreasing? OH minus is getting consumed in this reaction. Okay. So when the pH of the concrete at that interface between steel and cover, over there, if the pH becomes about 9, steel will start corroding. Steel will not corrode when pH is very high. Even people say at 10 it starts corroding. So different theory is there. But let's say for this class, we will say 9 is the critical pH. Okay. So when the pH of the concrete at the steel surface reaches 9, steel will start corroding. Okay. This is how it really happens. More detail on what it does. Okay. You can see that first the CO2, if there is enough moisture, it will form an acid. Okay. Now that also causes problem because you don't want acidic environment. That is why the pH is decreasing. Okay. And eventually you can also see that later CSH, which is the binder, that gets disintegrated. That means again, it is not something which you would like to have. Then eventually when the pH reaches 9, it attacks the passive film is not stable enough. We discussed that, the Pobbe diagram. This one here, when the pH reaches about 9, you see that on the horizontal axis, look at 9, draw a vertical line over there. Okay, so you see that corner over there, that V shape kind of at the 9, that from that point onwards to the left side, it is corrosion, the brown region, dark brown, brown region, right? So pH 9 is something which is very critical. You don't want a concrete with a pH of 9 or below because it will start corroding the steel. Now, how do we test it? It's very simple to test. What is to look at what is the depth of carbonation. Okay, you can see here, this is a cross section of the fractured piece of a beam, which we are exposing to various, with different type of concretes. So you can see here the peripheral region is colorless. If you go back to your chemistry class, +1 or I don't know, 9th grade, not 9, +1, no? Yeah. So chemistry class, you might have done some experiment where color changes from pink to colorless or colorless to pink. Titrator and suddenly it changes the color, right? So the pH, that 9 critical pH. So phenolphthalein solution, you can spray on the freshly fractured surface. Why freshly fractured? You cannot break it today and then come back and test tomorrow. Why? It's already going to react with the oxygen or moisture, everything available into the immediate environment. So you will not see what is reality. So you have to break and immediately test it. Spray this phenolphthalein solution and you can look at the color change, and that color change will tell me what is the depth of carbonation. So here the colorless region is carbonated concrete and the pink color region is the good concrete. So don't get confused with which is good and which is bad. Colorless is bad, pink is good. So you can remember this, pink is good. You put bindi here, no? Pink color. So some things like this is easy to memorize. Okay. Now here, this example here, it shows what? The steel is going to corrode or not in this example? About to. Because that second blue line over there, you can see that the top blue line, you forget that. Second blue line, the second from top, you can see that that is where the pH is 9, the critical surface. Okay. Now the bar surface is just touching that. That means it's about to corrode. Okay. Now in this case, which will be anode and which will be cathode? What do you think? The top surface of the bar, the thin line, will become anode. The remaining surface of the bar will become cathode. Because you have very small connect, you don't need additional bar. That's what I'm trying to tell. Okay, in the same bar, you can have both anode and cathode, and that will start corroding like that. Okay, but don't cut rebars when you take samples. This picture I got from one of the journal, but anyway, things happen. See, when you go test the concrete, you don't want to create problem for the concrete structure. So it's always important not to cut the bars. Okay. The chloride, I think, we'll cover after the lunch. We'll talk about this chloride-induced corrosion. So you can see different types of corrosion. See, bottom right corner. Okay, if you have been to temples and all that, you can see those kind of things. Have you ever observed, or anywhere, even in houses, you will see some railings made out of those kind of cement rich concrete. Have you seen that? Ornamental pieces made out of concrete will be rich in cement. It will have no resistance against. What is that element in concrete which gives the resistance to chloride ingress or carbonation? In concrete, which plays the major role in resisting all? What element plays the major role? So here, when you put cement rich material, you basically have no resistance, and that is right. This is from, if you have been to Chennai, from the Ashtalakshmi temple. If you go to the top of the temple, you will see these kind of things fully corroded right next to the ocean. Okay. If it's made with concrete, I can actually have it last much longer. But without aggregates, it's almost impossible to make that. Okay. But you aggregate means coarse and fine. I'm talking both. This is other example. It's again facing ocean. The middle building, on the other side of the wall, all the IAS officers in Chennai sit. Okay. On this side of the wall, they don't know what's happening. It's in the port. So the bottom right, what is the observation over there in that photograph? What do you see from? See or observe? What do you observe from that? How do you prevent that leakage? See, the pipe material is a brittle material. Okay. And concrete structure, there is always movements in that structure. You have to accept it. Now, your pipe, because it's a brittle material, when the structural elements, like in one sunshade and other sunshade, there are movements, it will actually bend and crack. It will not bend, but it will crack. So if your pipe is flexible, or rather not pure rigid material, then you will have no problem. So that's why nowadays, from cast iron to ductile iron, now we are using PVC or CPVC pipes. Cast iron will crack very easily, very brittle material. So later people started having ductile iron. Then you still, so in cast iron corrosion was not a problem, but the brittleness was a problem. You brought in ductile iron, then you have corrosion problem. Okay. So in PVC, what do you think we will have problem? What problem we will have? It has to be UV resistant because most of these are actually kept outdoor or external, right? Sunlight will be. So it has to be UV resistant PVC pipes. Can't just buy any PVC pipe. It will not last very long. So we are switching from one problem to the other. Okay. This one, you know, those ladies over there, they don't know where they are walking on what are they walking on. Look at the right side, how corroded that slab is. Yes, there is a extra, you know, steel beams provided, but for the sake of discussion, I brought that way. So we do again, that is not, see on the left side picture it's nicely painted, nice tile, well, you know, all that. So that's all cosmetic, but the skeleton is having problem on the right side. This is a you know, photo from a pharmaceutical company in South Chennai, where they were, the tank which you see there is actually H2SO4 and HCl. So all these chloride rich, sulfate rich environment, or acidic and chloride. Okay. So this building, literally I felt very worried when I was inside that building, because every single column and beams which you see in that building is replaced, or there is an adjacent steel element there. You can see clearly, look in that picture, top right, you can see that reinforced concrete element is actually replaced with a steel piece. Okay. So severe corrosion. But again, I feel this could have been addressed when you start seeing a crack, not wait until it starts cracking and spalling and all. We have now technology to prevent those kind of things. This is again a 5-year-old building where the structure is being replaced, or, you know, being protected by using galvanic anodes. I'll see if I can include a half-hour lecture on this in the next week, but otherwise we will see. Okay. Now, what is the type of water we should use? This photograph, if you can remember, forget about all the text, just the photo. This is the type of water you should use. If the MD of your company comes to the site, he should drink this water. He or she should drink that water which you give to concrete. Okay. I know it's a little bit impractical because we don't have drinking water properly. So that is where now we try to use treated water. Okay. So treated water also, the you know, I think the way out is to ensure testing. We know examples where RO treatment, I mean RO plant is there on the site, but doesn't work. So end of the day, you have to test water and also perform routine testing on the chloride in concrete, not only in water, because you never know who puts chloride into the concrete. Okay. So if you can test chloride in the final product, which is concrete, before paying the last bill. Once it is paid, then it's gone. Then it is defect liability period. that people will delay the paperwork so that you cross the defect liability period. On campus, things like that have happened. I know, because it's very difficult, bureaucracy. Nobody is blaming anybody, but that's what really happens. Okay? I always want to say I'm right. So I'll push the paper back into the other court. It will take another 1 or 2 months to come back. So by the time defect liability period is over and all the papers, so things doesn't work out that easily. So best is to control the quality and improve our quest for perfection. Quest for quality, quest for perfection. You know, one professor told me, because it's recording, I can't name the name of the professor, told me like in Indian construction site, you don't see straight line. Do you see? See this table, okay? Look at this table and look at the straight lines on the the table which you have. If you make it out of concrete, will you see like this? Will you see it today? Yes or no? You're sleeping or what? Huh? Yes or no? Low energy or high energy? You want to sleep, like I said, in the morning after full stomach? So now the question is, I'm trying to change a verb. I asked earlier, will you see, right? Now question is, can you see? Can you make it happen? Wow. Said yes, very fast. How? Huh? Precast, because you're sitting in this class. What is to do to make it in, even in precast it doesn't. You see that building next door? Even in precast today, we don't see that high quality. So let's be, accept what we are doing. So what is that we need to do to make it look good? Concrete should not look like concrete. It should look like a gray piece. Huh? 3D printing, no. This is precast concrete class. Yeah. Very good. I think formwork is the key. Okay. If you don't invest money and, if you don't have a good quality formwork, you will not have good quality product. Formwork, form release agent, those are the things where we need to work on when you talk about the surface finishes. I'm only talking about, those aspects, tolerance, surface finish. If those things are taken care well, your water tightness will improve. Okay, when you go out, you just have a look at again on the same mock-up building which we have right there. What are the imperfections on that? Column at the base and column at the first floor, it's not matching, it's not aligned. But we are okay with it. That's our resilience part. What is resilience? Huh? When come back? No. What is resilience? From damage or from something else? If you say resilience, if you have a stress strain graph, you want to calculate resilience. Until where you will go? To the right. Only elastic, right? So we don't say damage. It is not damage. That's why I'm okay with it. If it's collapsing, I'm not okay with it, no? Right? It's not real. I'm agreeing to it because it's a not having any permanent deformation. So within elastic limit, people, if I say, okay, no, you take out this column and put the back another one which will align properly, they'll say, no, goodbye, I don't want to work with you. Right? So there are those, because it's also money. So idea is to do things better up front, not after, but it's all learning. So anyway, so here idea is to test water and test concrete, not only water. We know examples where sea sand gets mixed with river sand and used on structures. So if that is the case, testing water will not help, right? So eventually you want to test not material, final product. Okay, materials, yes, that is the first check. The final product also need to be checked. Okay, so in chloride induced corrosion, what really happens is, like I said, in the case of carbonation induced corrosion, pH was the governing factor there. Okay, here, even if the pH is high, If the chloride concentration at the steel surface is beyond chloride threshold, you can have corrosion. So how it happens? Look at this picture here carefully. Those arrows, if you look at, they pass through the mortar phase, not through the aggregate phase, but in ITZ, like the interface between the aggregate and the mortar is the weakest location. Okay, within the, so it reaches some place because it's not a straight line path. So there will be locations on the steel where you get more chloride than the other locations at a particular time. You agree? Because it is not a straight line. Speed of chloride penetration is different at different locations. So at some points you'll get more chloride than the other. So the first point where you get more chloride than the other will start corroding. So that's why you have preferential corrosion in case of chloride induced corrosion. Okay. And once an active cell forms, it's very difficult to change that, stop that corrosion and another one will. So it will keep on, so you'll have pitting corrosion. And there is also one more reason, because it's a little bit acidic nature is there in this chemical reactions. If you look at here, let's start with the second blue box on the right side. Okay. Second blue box on the right side. So where you can see chloride ion, 2 chlorides, right? Now that plus Fe2 plus, which is available from the previous reaction, and that will form ferric chloride, and you have an acidic environment which is the H plus from the HCl which is written on the top. Okay, so you'll see this is a catalytic reaction. So but I'm going to start from that 2H plus plus 2 chloride, and that chloride will precipitate and it will form more what? Fe2 plus and 2 chlorides. Now the point to make here is I don't need more and more chloride implement in large scale. Maybe one-off structure you can do. As a technology, it is good. I'm not saying that. But for implementing on site, it's very difficult, very challenging and costly. Okay. So chloride-induced corrosion, once it starts, it's catalytic in nature, and you can't really, it's difficult to stop unless you treat electrochemically. Come down to the bottom right blue, again you have H plus and 2 Cl minus. That is not a new Cl minus. That is the same Cl minus which is there in the other boxes. So it keep going. Okay. Now how does it look? If you see a rebar with corrosion, this is how they look. If it is chloride induced corrosion. If it is carbonation induced corrosion, it will not look like this. It will be smooth, layer by layer removal is what we experience in case of carbonation induced corrosion. Okay, so you can see the pits. So in this picture, if you imagine that strand over there on the top, it's like a close up of a volcano, that one pit at the center. Can you see that? So it's very clear how that pit. So that why it is pitting, it's because of this HCl on the top right. So it creates that acidic nature at the center of the pit, and then it keeps growing there. Okay, pit keeps growing. At the bottom one also you can see some locations with lot of corrosion, some locations without any corrosion. Strand, it is very clear. There is pit, and there are other locations where absolutely no corrosion. You can see in the strand photo, bottom right of that photo, you don't have any corrosion. Bottom right. So same strand, it's in same concrete. Okay. So what type of corrosion is this? Micro cell, macro cell, what do you will call? Strands, usually you put it in high quality concrete. Resistivity would be, this particular specimen is from a high resistivity concrete. Okay. So micro cell. Now cracks, also a big problem. Anything about any doubt on chloride induced corrosion? I can't hear you. Here means? Yeah. Rust is increase in volume. Both. Doesn't matter what. See, what is corroding? Steel is corroding, right? So if you look at that phase there is no chloride in that. Do you see anything chloride on the left side? Any carbonation on carbon dioxide? It's all different phases of iron. So the other slide I said, no, like it's assistance. Chloride and carbon dioxide are they don't take part in the corrosion reaction. They just provoke steel to corrode. They create the problem, but they don't actively participate in the problem. Is that clear? Okay. So corrosion reaction, it is moisture and oxygen. That's what take part in the corrosion reaction. This one, essentials. If you look at anodic reaction and cathodic reaction, you will see moisture and oxygen. That's all. Okay. You will not see chloride or carbon dioxide in the anodic cathodic reactions. You will see them in the things which lead to corrosion. Okay, cracks. So this is very, very common, right? This kind of cracks, people from the site, definitely you must have seen tons of cracks like this. One reason, you remove formwork earlier. You save money on cycle and spend money on repair products. Because to inject, how much it costs to inject one crack, like with epoxy or whatever grout you use? At least 500-600 rupees per meter per nozzle. So that's very, so if you wait for few more days and cure the concrete better, you don't have to do that. Okay. So, but people will say remove it, use it elsewhere, because planning engineer will tell you to do that. But planning engineer should also have a column for the planning for repair. So that's a challenge. So the again bottom left picture, this is from a hospital building, 7-story hospital building. You see a prop, do you think that will support that beam? Do you think? The other day I saw, like last week, 6-story building, on the ground floor, they put a prop like this. And you know what is there? There is in between the steel plate of the prop and the concrete, there is a wooden piece. So what do you think is the problem? Why are we providing prop? It's not support. To reduce it, to de-stress the element. Okay, to reduce the deflection or to de-stress the element. I don't want any stress on that element, so that's why I'm doing it. Now you put a prop and a wooden piece over there. Do you think it will de-stress? It will just get compressed. The stress will still be there. So these are a lot of such things happen in our sector. Okay. So on the right side, you can see, if those little icicles kind of thing forms on the. Have you tasted, any of you from the site people, if you're seeing those things? Have you seen that? Have you tasted? No? Well, basically no taste. We have tried that in Research Park building. 10 years ago, I took students to, so in Research Park, they did the same thing. We will go tomorrow to the building, but they removed it. They removed the formwork early, and it was also cracking. And then you can see this icicles. Eventually, it will seal because you will put nice tile on top. You will put nice painting on everything. You will cover up everything with additional investment of money. So, if you can plan a little bit better, you can avoid many things on the site. Coating after coating after coating. Now, if you look today, any construction, you will see waterproofing, multiple layers of waterproofing coatings. In IIT campus, like right now, we spend a lot of money on waterproofing. Essentially, we are putting raincoats on buildings, PVC membranes. Many of the buildings have raincoat on top, literally raincoat. 2 to 3 mm thick PVC membranes are put on the roof. On top of everything else is just covering. Very costly affair. Now, the new construction, do we need all that actually? Salespersons will come and sell the material to you. Okay, in today, like you have to actually, you engineers have to decide whether I need that or not. My opinion is, do good concreting. If you do it, you don't need that. Maybe a little bit on here and there, if at all there is a crack, but you don't have to cover the whole thing with the waterproofing layer. It's not required. Typical waterproofing applications, also you need to focus on the joints, not everywhere. You don't need everywhere. But okay, that's different topic. Shear crack. Here again, you can see it's actually a pre-tension concrete beam. A major highway in Mumbai. I took this picture like 10 years ago. Okay, today the whole thing is fully painted with blue color. So you don't even see any of those cracks. Do you see the cracks? Do you see shear cracks on that? The bottom left is very clear. No, every single, about thousands of girders have this problem. But I think, I don't know when corrosion, every time when I go, I think look at it. But I mean, I'm just showing real example problems which we have with respect to durability. How do we design now? Now we know all the problem. I have a corrosion problem because of chloride induced corrosion, carbonation induced corrosion. Now, how do I choose materials and all that? So this we discussed earlier. So I have so many materials available in the market today. Okay. Now, different type of steel, different type of concrete, whole lot of chemicals. Okay, all these are available. Now, what do I look for is, now in this lecture, I'm going to talk about the steel which we have, TMT steel. Okay. Now, I written as QST, not TMT. See, there is no steel in this world which is made without a thermal and mechanical treatment. Any steel you pick, it goes through a thermal treatment and a mechanical. Then why do we call it thermomechanically treated steel? Story goes like, somebody in SAIL, when this was introduced in the Indian market, they started talking about, and somebody wrote thermomechanically treated and everybody followed. Like Maggie, we used to call Maggie until the other players came into the market. Maggie was actually noodle, first noodle. Okay. Now Top Ramen and then Patanjali, all that came. So Maggie, they might have filed a case or I don't know how. But the thing is, we go with this name and whoever starts and then, so this is, there are a lot of patents on this with slight modifications in the procedure, but essentially you get a steel bar which looks like what the picture on the right side. Cross section looks like this. Okay. All our TMT bars or QST bars should look like this if it is ideal one. What is like this means you have a peripheral region which is full ring, which is tempered martensite. Okay. Which is strong, very strong material and hard material. The middle one or the core is the ferrite perlite, which is ductile in nature. Because you want, why do you want ductility for the rebar? Earthquake resistant design. Okay, for that you need ductility. Why do you want hard surface? Because you're roughly handling it on site. You don't want it to get damaged by hammering, all that. Okay, it's a construction site. So how is this made? If you look at the top image, you can see that on the horizontal axis you have time, and vertical you have, or ordinate you have temperature. What is the starting temperature? The molten steel. What is the starting temperature? Around 1000 degrees. And in 1 second, the surface temperature of the steel becomes how much? 200. So quenching. They do quenching on. Remember blacksmith, what do? They quench the knife edge. Otherwise, what happens? You won't be able to cut bananas even, or because the moment you hit on the table, it's going to blunt the knife edge. So you need what property you are looking for that knife edge. Sharpness is there. Hardness is very important. Okay, toughness also. So you need that hard and tough surface, then only it will work. So we need for rebars also, we need that thing, and that is why we are quenching. So it's essentially TMT bar is a composite material. If I can play this video, yeah, this is how the TMT bars are made. Playing but no sound. So you can see the red line is the TMT bar. Very fast it moves. You can't even see how fast it is, that fast. Okay. Now these are the, you can see this is the quenching box. The red line is the rebar, hot rebar, and you spray water onto it inside this quenching box. So the entire surface of the bar gets water for 1 second. So the bar passes through this at that speed that it's only over 1 second it gets water. Okay, sprayed onto it. So this, you see the cross section changes like this, and just waiting for it to come. So in 1 second you get the surface temperature as 200 degrees Celsius. Okay, and that's what this is how it looks like, the final bar. Okay, and it's not microscopic image. When you look at it, you can actually see it. I'll show a video now on how the color difference is. Now this is how why we say TMT bar is essentially a composite bar. Okay, what we did here is we took a 32 mm diameter rod, and then we took a cylinder from the peripheral region, which is TM, tempered martensite, and did a tension test on that, and then another cylinder from the core, did a tension test on that. Okay, so from the, so you can see that this solid curve, which is tall and short, not that wide, narrow, that is for, by looking at the legend, what do you think? You are all sleeping, so you have to tell what is that graph. High strength and low ductility. Okay, that is the peripheral or core? Peripheral. The core is FP, the dotted one, which is not high strength but very ductile. That is the core. Now what your bar is, the middle one, which is the composite action. Okay. Now the area of the peripheral, the tempered martensite, the area of the ferrite pearlite will determine where the center curve is, or the composite behavior is, and that area will be determined by the quenching action. Okay, how well you are quenching the bar, what is the time through which the bar passes through the quenching box, so that will determine. So this, okay, so issue is with this bar. So, how this evolved also I should probably tell. 10 years, 15 years ago when we started this testing, CTD bars, the earlier bar, the high yield strength bar, which we say HYSD bars, they are supposed to have, or the TMT bars are supposed to have low corrosion rate than the CTD bars. Am I correct? Correct? Don't drink water and come. So CTD bars are, that is why TMT bars came into the market. The CTD bars are cold, twisted, deformed bars. You can write it, cold, twisted, deformed bars, where the spine of the bar looks spiral. I don't know if you go to a structure which is like 20, 30-year-old, you will see the spine is not straight line. Ribs and spine, that on the bars we have ribs and spine. You agree that? The one which is transverse, we call it rib, and the one which is straight, we call it spine. Okay. Now the old one, they were twisting the bar during the making. So that spine were spiral. Because of that, it was corroding more. So people came up with this TMT business, which is actually corrosion resistant. So we collected a lot of bar. We are doing a testing in the lab, and then we found that actually TMT bars are having same corrosion like the CTD bars. There is no improvement in many of the products in the market. Then we looked at why it is not showing good corrosion resistance, the TMT bars. The reason is this. When we did the TM ring test, we found that there is actually no ring on the bars. These are crescents, not rings. Ring means it has to be full circle. If it's disconnected, it's not a ring anymore. So then we found that actually the quenching process is not done properly, and you have bars like this floating everywhere in the market. Okay. So then we tested. How do we test? How do we know whether there is ring or not? So you can cut a rebar piece, and you can just, this is called etching, acid etching. Okay, you put that 5% nitol solution. Very simple test to do. Maybe we'll show you this in the lab also next week. So you can see on the left side, no ring, on the right side, full ring. Okay. No SCM or anything. It's just direct view. It reacts with the tempered martensite, and then it basically etching. It eats away some, and then that you see the color difference. So the ferrite perlite shows light gray, and then tempered martensite shows the dark gray. Okay. So when I saw this, then I called a prof in Germany. I asked him to give me, because this was really surprising to me. And I asked, so when I called him, and then he said, I told, sir, I need some TMT bars. He said, what is TMT? That's where I also started thinking, why are we calling TMT? So he said, over there, it's all QST bars. Out of India, we call it QST. Within India, we call it TMT. Okay. Now that we are changing the code, slowly you will also start seeing QST. Now, and we got a lot of bars, and we found it's only in our products. All the European products have very good ring, whatever we test. So it is doable. It's not that it is not doable. I'll show you that also a little bit. Now, okay. So the one on the left side is a good bar. Okay. Remaining with red dots over there, which shows inadequate ring, that is actually regions with poor quality, or that is where you can have galvanic corrosion. Why? Because you have two metal faces, dissimilar metal surfaces, in contact with the cement or concrete. So you can have the corrosion cell. Small micro cells can form where you see the red dots. Okay. This is probably one of the reasons why our structures built with TMT bars are corroding. and they corrode where the bend is. I'll show you that also. So we tested many products. You can see on the top line, it's a small diameter bar. Then you have the larger diameter bars. Now, if you ask a company, they will show you the big one only. Because in the look at the bottom one, you have 4 out of 5 are passing. You can see, no, the ring is good. As the diameter is smaller, it's difficult to maintain the ring or develop that ring during the quenching. Okay, or may not be difficult, but they neglect it because it's like a small chota bacha, like small baby. Why do we worry about it? And in steel industry, this was a case. I was told that even the largest manufacturers in the country, they used to outsource the small diameter bar production. They used to make only large diameter bars, even the big ones, because there is not enough money. So you ignore the smaller one, okay, because money based on the weight. But now we are realizing that the small ones are the one which cause problem, or most of the corrosion is happening on the stirrups. Agreed? Why? Because smaller? No, not because it's smaller dia. Cover is smaller. Stirrups will be outside the what bar? That's why I asked what bar. You can't call it main bar. Do you check shear resistance when you do structural design? Is shear check less important than flexural check? When you do structural design, is shear check less important than flexural check? Importance is same, no, for both. So why do we say on one as main bar, which is taking care of the flexural, and not the other? One is main, that means the other is not main, right? So my suggestion is, let's get rid of this main bar business. We need to probably call lateral reinforcement, longitudinal, or longitudinal and lateral or transverse, something like that. Because many places I see main, people say the main bar because it's bigger. Bigger, it costs more money, it's large, those are. But technically speaking, both are important, and we are having problems with the smaller ones. So if you bend the bar with poor quality TM ring, you will see something like on the right side. What do you see? The TM face is peeling off, but on the top left, it is not peeling. Top left is like a proper ring. Okay, so the stress distribution is very even in the left side bar, even when you bend. Whereas on the right side, I have two material with two different stress strain graphs, right? So when you bend it, it's actually peeling off. And now when you have peeled off bent bars like that, you don't need chloride to cause corrosion. All you need is this whole phenomena of corrosion in the top, in the right side case, is crevice corrosion. Maybe you can write this. I didn't put that word here. Crevice corrosion, because you have a gap there. So when it peels off, what happens is, let's say this is the bar and then it peels off. So I have a very narrow gap. In that gap, you will have crevice corrosion because of the difference in the oxygen concentration. Okay, it's not very important. You write this word. If you are interested, you can read, because I don't want to pump in too many things into the head. Okay, but point is, you don't need chloride to cause corrosion in these bars. Mechanism is different. Okay, and this is what we do. All our earthquake resistant designs, we need how many degree? What is the degree? 135. When you do that, you have cracks like this. Our code says bar should not crack, but nobody checks. Right? So exactly where that bend is happening. You can observe next time when you do at site also, you observe, and if it is cracking, you have to reject one lot. Okay, I think this is the reason for most of the corrosion in many of the structures which we have, plus of course low cover. We have it in the code written, but we don't do it. Which one? The rebar, I don't know if we have. We don't have it. That we, I don't know for the rebar if it is there, but we can. Yeah, that's what. When you talk about steel, we test only tensile strength, one number. We don't test modulus. I have seen test reports which says modulus says 200 GPa. Test report. You know what it means? Test report without actually doing the test. So you get those numbers exact 200 because it's difficult to test. Modulus is not something very easy to test. Okay, it's very difficult. But if it is difficult, better not to write it. If you haven't done it, you should not write. Okay, so this TM lack of proper ring also cause problem with the rebars. Sorry, a problem with the yield strength. So it's not only corrosion, even in the mechanical properties, you will have variations. Okay. Now I tell all this problem, but this is a very recent work. We are seeing how to tell, because 60% of the bars manufactured are not by the major companies. 60% of the steel bars in India is not manufactured by the major companies. So if I say all your bars are a problem, they'll all come and do something to me. So we have to also find solution. It's not only, see, our job is not only to find problem, we also have to find solution. Okay. So what is the role of an engineer? We have to identify the problem. That's also our job. Identify the problems and then find solution. Okay. So here you can see that what we did is in one of the plant, the quenching box, you have to really clean it very nicely. This is how so what happens is many places they don't check because in the standard there is no need for checking a TM ring. In our standard, current standard for steel bars, there is a section which says how to test the TM ring. Okay, but explicitly it says based on this test you cannot reject a bar. It says explicitly. Okay, then my question is, why do you tell all these things if I should not use it? So why it is? Because at that time the standard was made by manufacturers. You will see that many of the, if you're talking about a cement BIS code for cement or for steel, product manufacturers will govern it. They will be having an interest in being in the committee and then do it. Now it is moved to user side. Civil engineers are now deciding how the bar should be. Earlier it was heavily done, I mean it was done by MTD, metallurgical department. So these are slowly we are also learning and changing things. Okay, so this will be there in the new code. You see this again. You see it's a top brand. You see that bar which is bent on the top left. Can you see the crack? Top left and top right you can see. It's a good quality bar, but it is bent 90 degree. Because the mandrel diameter used is wrong. So if you can imagine, if I bend my finger like this, what will be the stress on the outer tension? So let's assume a magnitude of for that stress, okay, or strain. Now, if I bend like this, over here it will be much higher, right? So you are supposed to not use a smaller diameter mandrel, you are supposed to use a larger diameter mandrel. That diameter is dependent on the diameter of the bar. Now, why I'm showing this thing is, in the current code, people say you should use different mandrel diameter for testing the bar. It doesn't say for using the bar on the site what you should use. And people are misusing it. I don't know if you got what I'm saying. If you are testing a rebar for passing, like, for qualifying a bar, you will use a proper larger diameter mandrel. So the bar will not crack like what you see. But on site, on actual construction, you will use a small diameter mandrel. So what will be the bend angle? It will be like pakka 90 degree. And then you have cracks like this. And this is a major bridge. It's covered by concrete. It's all done. So things which we think are not very important actually cause problem when it comes to long-term performance. Not for design for commissioning, but for design for durability. Okay. I think I'll stop here and then next. No, if you have a proper plateau, then you don't need to. But mostly in TMT bars, that one was actually small diameter bars, because the ferrite perlite was so high in that, not the tempered martensite. The combination is what gives you the I know what you're telling. You're saying that perfect horizontal line. Yeah. But if you take a larger diameter bar, you will not see that much. Oh, sorry, yeah, you're correct. Ferrite perlite will have proper yield and not the tempered martensite. So in the composite action, you will have kind of a mix. Larger diameter, you will have more well-defined, But I think still today we are telling to go with true stress on, because see here I am able to plot that graph because I have very good instrument. Otherwise, I cannot get that graph. Okay. So this slide is familiar. So what do you observe on this slide on the right side? It's a resistivity of the concrete. Okay. What is the difference between the OPC concrete, which is blue color, and the fly ash and slag? Let's forget about the remaining three. Okay, only blue, red, and green. Upper limit on OPC, how much it is? Roughly, you look at the screen and tell, or your printout which you have. 30, no, 20, no? There is only one value which is about 20. Right? Yes or no? Yes. Now, in the case of fly ash and slag, there are so many numbers which are about 20. This is the biggest advantage of fly ash and slag. You get a concrete which is highly resistive. Now, if I say highly resistive concrete, the yellow region here is highly resistive. Now, what does it mean in terms of corrosion rate or ability to corrode the steel? It reduces. Even if corrosion starts, the rate will be less. To initiate also, it will be difficult. So it's always very good to have highly resistive concrete. Electrical resistance of the, or electrical resistivity of the concrete has to be very high. So the red one and green one with fly ash and slag, it is very easy to get more than 20. Whereas in OPC, you really cannot get more than 20, 25. It's very, very difficult. So if you want to really talk about durable concrete, go for fly ash and slag and specify in that my concrete should be having a minimum resistivity of this much. Right now we are proposing a resistivity of 30, because if you say 30, you will have to put fly ash or slag, otherwise you can't get. Yes, we have some sort of empirical relationship is there. Yes, yes, yes. It's not the filler, it's actually no, it reacts with the calcium hydroxide in the concrete. So calcium hydroxide phase, which is, I would say, the weaker phase in the regular OPC concrete. So that calcium hydroxide reacts with the fly ash, which is rich in silica. Now you have calcium hydroxide and silica. So you can produce more CSH, which is the binder or the glue in the concrete. So your concrete with fly ash or slag will have less air voids, okay, and it will be more compact microstructure, so it will resist the penetration of chloride, carbon dioxide, etc. Okay, there are different for this class, that is a good definition. Okay, especially for chloride, it's very highly resistant. Carbonation is a different story, but so now when you have this kind of highly resistive concrete, we usually see micro cell corrosion, we don't see macro cell corrosion. Okay, I earlier mentioned the micro cell, macro cell. Okay, so basically you can have a small region with chloride and corrosion can happen right there. I don't need another bar to support me to actively corrode. Okay, let's forget this slide. Let me just skip. So last hour, few PhD students have worked on this chloride threshold. So this graph, it took 15 years to make. Okay, of the chloride threshold value, which I said as boundary condition, the minimum amount of chloride required. So what you're seeing here is, historically people used to say 0.4 is the chloride threshold, but now with new cement and new steel coming into the market, this value is changing. So some sort of estimates we have on this chloride threshold of various steel cementitious systems. Okay, not only steel, but what I mean to say is, if I put a steel in OPC, I might have a different chloride threshold than when I put it in fly ash based concrete or slag based concrete. Okay, now for pre-stressed concrete, we generally see about 50% less chloride threshold. So it's more dangerous, or rather more concern when it comes to pre-stressed concrete, because it's under stress. Okay, I don't know if you noticed today where you had the tea break, did you see any broken anchorage? 12-year-old piece. That bridge was designed for 100 years. Okay, so that was a pre-stressed concrete element, a pre-stressed steel. Okay, so when you have the stress, it's like this. Imagine you have a rubber band. You pull it. What you will observe when you pull a rubber band? You will see some micro cracks forming. First micro cracks, then larger macro cracks. No, you slowly pull it, you will see the slowly new and new cracks are forming. So pre-stressing steel is also like that. You pull it, you keep it there. When some chloride comes, it will find its way through the steel and go in. Okay, so it can also have, it can have more problem than a regular steel. It's more vulnerable to corrosion than regular steel. Now there is also other chemical which we use in the market to increase the corrosion resistance, which is corrosion inhibitors. These are some chemicals which we mix with time. How much? 330, right? Up to 330, right? So yeah, so corrosion inhibitors you can use. It helps to improve the passive film. What was the thickness of passive film we talked about? In what unit? Angstroms. Okay. So that these inhibitors will densify that and it will make it more resistant against the chlorides. And it's, very promising, but it's difficult to convince somebody to use this. I'll come to that point later. Why? So this is a parametric study we did earlier. Jayachandran did it. So you can see almost 3 times increase in the average service life with and without inhibitors. I'm not telling you to take this slide as it is, but what I mean to say is that it is very beneficial to use inhibitors. This is from Jayachandran's PhD. This is, but one problem with this inhibitor is why people don't really use is because there is no vested interest on contractor's side. See, if you don't use, let's say somebody give you mixed design and then you have super plasticizer as one of the chemical admixture, right? What is the purpose of using super plasticizer? To make the concrete workable. If the concrete is not workable, you will not get the money because you will not be able to place the concrete. So the people at site has a vested interest in using super plasticizer so that they can finish the work. So that concrete will flow and go, right? But inhibitors, the action comes when 30, 40, 50 years down the line. So I have no interest actually, right? So, I mean, I am not generalizing it, but what I mean to say is this is one concern. Because whenever you talk about any corrosion resistant mechanisms, the action comes much later. That's also there, but what I'm saying is there are many other which are only inhibitors. I have heard stories where barrels, empty barrels of inhibitor move from one site to another site. When an inspector comes to one site, there is an empty barrel of inhibitor. He goes to another site, the barrel goes along with him. But super plasticizer, it will not happen that way because you need to use that to finish the. Okay. So inhibitors generally, when you use fly ash and all that, you have some issue with the chloride threshold. Okay, it will kind of reduce, but eventual effect is different. This slide is not something which you have to worry about. Chloride threshold, better chloride threshold, like increased chloride threshold is better or reduced chloride threshold is better? Huh? Why there is a confusion on this? Higher chloride threshold is better or lower chloride threshold is better? Higher chloride threshold is better. But when you put fly ash and slag, there is a tendency to reduce the chloride threshold. However, the service life is dependent on how long it takes for the chlorides to reach the steel, right? So the speed by which the chloride travel through the concrete cover also matters. So it's a synergistic effect. It's not only chloride threshold. It's an effect of combined effect of diffusion coefficient and chloride threshold. Am I talking it, is it speed is okay or huh? Okay. Because one thing is the speed by which the chloride goes through, other is how much chloride you need at the surface of the steel. So in one case, let's say I need 1 unit of chloride to initiate corrosion. Other case, I say I need 2 units of chloride to initiate corrosion. Okay. Which one will start first? Tell me. Huh? That's the answer. There is no answer for this question. It depends on time to reach and build that quantity. So in this one unit case, if my speed of penetration, if let's say this one I used a concrete which has x is the speed, and in the 2 unit, if the speed is much smaller, then probably this will initiate first, both speed and the amount of chloride you require, combined effect. Food for thought. Think later. Okay. So that's what you're seeing here. Okay, in the fly ash, it is possible to design and increase the service life by more than twice. So I know there are a lot of people who talk about fly ash is not good. In some sites, I heard people saying pure OPC, like pure vegetarian restaurant. They say pure OPC, thinking that adding fly ash is not good. So they say, okay, it's not just OPC, it's pure OPC. Okay, but it's exactly the opposite. We need to move away from OPC. We have to use it's high time that we change our documents and and start using fly ash and slag. But it's an old story now. See, today we have standard products, PPC, factory produced products. It's available. So this was a concern earlier. In bags, like not fly ash. I'm saying the Portland pozzolana cement, it's pre-blended. It comes with, so in your retail market, I think it's already there. It's only in the, major projects where we still have struggled to. Now the inhibitor, see, one thing is this, inhibitor, you are actually putting it in concrete. So it can affect the property of the concrete also, not only corrosion resistance. If it does something to the corrosion resistance, maybe it will also do something to the concrete. So you have to think about whatever you mix in concrete, what it does to the steel and what it does to the concrete. Both have to be looked at. Not only what it does to the steel. Usually when corrosion products are marketed, or corrosion resistant or corrosion enhancing products are marketed, they talk only about corrosion. But does it make sense to test the concrete with that chemical if you are actually mixing that chemical to the concrete? So what you see here is the green box over there is the recommended dosage for a particular inhibitor. The red ones are when you deviate from that recommended dosage, the compressive strength of concrete dropped. This test I did 3 times just to confirm. So dosage is very important. Yesterday you might have seen, no? What was the problem yesterday in SCC? It was not SCC, right? What was the problem? Did you ask? Today you ask, okay? Why it was not SCC? Because today Umesh is making, team is working on ensuring that it really flows. So yesterday they did not consider the dry aggregate, the water content. So the aggregates absorbed all the water and it was not available. So moisture content of the aggregate is very important. Coarse and fine aggregates. Otherwise, the water will be absorbed by the aggregates and it will not be available for the cement. So that's what happened yesterday. Mixed design was good, but moisture correction was somehow we missed it. Okay. So dosage, any chemical you put, the moment you change the dosage, it can behave very different. Okay. So this is an impact of the change in dosage on mechanical property. This is the impact of change in dosage on water sorptivity, or which is a durability property. Okay, so you can see, I mean, some boxes in the first 2, you can say there is a change in the quality. How do you read this graph? one is control, a recommended dosage. Okay, you can see that once you put the inhibitor, the sorptivity is going from, in the blue case, what is happening? Sorptivity is going from what category to what category? Look at the table on the right side. From poor to very poor. It's changing. So inhibitor is good or bad? Bad. Second case, also it is changing from better category to a worse category. But these two inhibitors actually showed better corrosion resistance. So we have to look at both the aspects, what it does to the steel and what it does to the concrete. Anything you mix in concrete, you have to look at both the aspects. Okay. Yes. Only on the steel surface. No, steel surface. The rebar, that is where the passive film, that's a challenge. So this is a very good point, because 90% of the inhibitor is waste. Or even more than 90%. If you look at the volume of inhibitor which is actually working on protecting corrosion, preventing corrosion, it's very, very less. Imagine a metro pier, you have, let's say, 2 meter by 2 meter, and you have whatever reinforcement, you add the area of contact with steel and concrete and the chunk of concrete which is inside. It's all wasted. There are products like that. They call it differently, but there the main challenge is you already have rust on that, and then getting good contact and all that is a big challenge. So here, this is exactly that point which you were talking about. Action is only at the surface. So can we actually have an inhibitor like you were saying in SP plus CIA? Then people will buy and use it. Okay, this is okay. Other thing is fusion bonded epoxy coated bar. Okay, now most of the place you say epoxy coated bar, fusion bonded. So it's not in that it need to be fusion bonded. See this picture, a lot of cracking, peeling, everything is there. You can also see sun. That means that sunlight, and considering the delay, takes several months for another concrete to come. So all that time it's a problem. UV ray, where is India? What is the rate? Greater than 10. Okay, what belongs to very high to, so we have very high. Okay, so if this second picture on the top, why it is cracking when it is ductility, and it became brittle because it was okay. Now the second mechanical damage, second picture, that is basically you dry the entire bar. Okay, UV issue. Now we did some tests, found that when we kept the bar outside the lab, also found when we kept outside the lab, it was cracking. Not bending, and just like that. Look at it with your naked eyes, it looks very good. Put it in the microscope and look at it, you will see a lot of. So the 4 images over there, the first two any cracks. Second one, if you look very carefully, you how many days? UV chamber. But third, again you have the crack is growing. I had another picture, I forgot to put that in this, but bar from just kept outside in 45 days, we are cracking. Now, is this crack big? Even if I don't see it, water molecules can easily go through those cracks. Okay, so we are dealing. I am worried whether what at home on your gate do you paint? No, normal. We do or not? Do they corrode? If it is paint, why it is corroding? Because of UV. Paint is not UV resistant. It will cracks. Visibly, you will not see it. Okay, but it will have micro cracks, and this is our problem. Bar. And when we did the analysis, good quality epoxy coated bar, if it gives the actual epoxy coated bar, which is cracked and is there, it will give you less than an uncoated bar. So why do we spend 33% more? On an average, now it is 1/3 more. Cost is 1/3 more. You pay extra, get inferior product. Okay. So anywhere if you see epoxy coated bar, just say no. It's not good when it comes to durability. Okay. You can see that that black line is the uncoated bar. I think black is the uncoated bar. Yeah. And you can see the blue, which is scratch damage. The life is around, let's say 40 something, 35. Black one is giving me more than 50. Why? Because when you have a scratch, the mechanism is again crevice corrosion, like I said earlier, cap, right? Let's say on your vehicle or in this bottle, if I put a scratch here, where it will corrode? On the scratch. So what is the anode cathode ratio? High or low? Because the scratch becomes the anode. Okay. So I have a very high anode cathode ratio or very low anode cathode ratio. Which you pick, whether you want to talk about anode cathode or cathode anode. Cathode anode. Okay. So I have a very high cathode anode ratio when I scratch it. That means high corrosion rate. Okay. Corrosion starts with C, cathode starts with C. So this is the problem. So when you have scratch systems, it doesn't work. Now the new one is, let me skip this, galvanized steel. That's metallic coating at least. It won't scratch as bad as epoxy coating. Okay. Two types of galvanized steels are, the right one is not there in the market, widely in the market yet, which is a thinner galvanized steel, but I just want to give you a flavor on that. I don't want to talk more, but the galvanized steel is better than epoxy coated bar. At least it's metallic. So these are the properties which you should look for when you talk about coating for bars. One is has to have high resistance to scratching or abrasion resistance, high UV resistance. Of course, you need to have chemical resistance also, corrosion or chemical, and peel off resistance. Because at the site, you will peel off the coating, you can scratch the coating, and sunlight is there. All these are very important to consider when you think about coating. Why I am saying this, in today's construction market, there are numerous types of coating available. Sometimes people come with saying coating which is like, almost like rubber. You touch it, you feel like you're holding a rubber piece. This will not give you the any at the rough handling at the site. We are not treating bars like babies, no. So we are treating them very roughly. So we have to consider the exposure condition. When I say exposure, I am not talking chemical exposure. Whatever the material is subjected to, the rebar is subjected to. So that's very important. From here, I'll cover later. Okay.